So this little video is going to review with you how to decide when to reject the null hypothesis. And this gets crazy with the language, but you will get used to it as we work with it this term. To help yourself to answer this question, you should draw for yourself a little curve like this and mark in the z numbers, the 0, 1, 2, 3, and -1, -2, -3. So you'll recall that in step 1, when we parsed the problem, we always had the research hypothesis. I'm going to abbreviate that a little bit here. In fact, we usually will abbreviate it as H1 or HA, which states that population 1 is, let's say, higher, whatever we're measuring is higher than population 2. And we always have the null hypothesis, which we call H0, and that's that population 1 is not higher than population 2, or we might just say is equal, no different from population 2. And generally, this one up here is what the researcher hopes for, will be happy about if it happens. Usually a researcher wants to show that that population is different. So in order to make your decision, you'll need a few pieces of information. You will already have most of the information you need because let's see, in step 1, you determine the tails of the distribution. And in this example I gave here, we're looking for a one-tailed high test, which we all know. I can tell because we want population 1 to be greater than population 2, which means that the researcher is looking for a score somewhere in this region. And you'll need to know alpha, which is also stated as the significance level. And that's the odds that the researcher wants in order to, like, how comfortable would he be with error? How certain does he want to be? It's going to be stated in the problem. And you already went through this in your last test. It'll be stated in the problem, and it will be alpha equals 0.05 or alpha equals 0.01. So you'll need that piece of information. And of course, by now you will have used that piece of information in step 4 to determine the cutoff point. So the cutoff point is the z-score associated with that level of alpha in that test. And so let's imagine that in this case, we have a cutoff z-score that we'll call z alpha, z-score associated with alpha. And if it was a 0.05 probability level, the z-score would be 1.64. And you worked on this in step 3. And so you worked on looking up the cutoff point. So if this is the cutoff point, then we mark it onto our chart. Here's the 1.64 right about here between the 1 and the 2. All right. And we'll put ZA equals 1.64. And then we went ahead in step 4 and we calculated our z-score. So we'll write our sample z-score. We'll just put z, and let's say it is 1.88. We plot our sample z-score. So we know once we do that, that this entire region, any score that falls in this shaded region will allow us to reject. All that shaded region is called our reject region. It allows us to reject the null hypothesis, and the researcher is happy. We'll look at why in a moment. And all the rest of the distribution, all this white region, means that we're going to fail to reject the null hypothesis. And so here we can go ahead and plot our sample z-score, which is z equals 1.88. It falls into the shaded region over in this tail. Since it falls into the shaded region, we can reject HO So our decision is to reject the null hypothesis. And when we make this decision, we can, in our minds, cross it off. And if we cross it off, the only hypothesis remaining is this research hypothesis. The researcher is happy. Let's look at another quick example then. So I'm going to erase much of what we have here already. And let's imagine that we have now, we still have our null and research hypothesis, but now they're a little different. There we go. Get all that ink out of there. All right, so now let's say that our research hypothesis, this time I'll just write H1. We can say H1 or HA. And the researcher just thinks that population 1, actually, let's say the researcher thinks that population 1 should be lower than population 2. And of course, the null hypothesis is that population 1 is not lower than population 2. And you can also write equals in here if you want. So here are our hypotheses. So now let's go ahead and give some condition. So let's say this has alpha equals 0.05, and it is one-tailed low. And actually, let's make this one be alpha 0.01 with one-tailed low. And we know that in this condition, the cutoff point, or the, let's write cutoff point, Z alpha, the Z-score associated with alpha is negative 2.32. We know this from looking it up in that online calculator tool. And we know that our sample Z-score, we calculated it out and we discovered that it was minus 2.08. Now, we have some certain things we know. We know that in a one-tailed low test, we're looking for something down here to allow us to reject the null. Where do we draw the line exactly? Well, we draw it at Z alpha, 2.32, something like this. So it's got to be something more extreme than that in order to allow us to reject the null hypothesis. Here in the tail of the distribution, we have the reject region. And the rest of the distribution is all the fail to reject HO. And we find now that our sample Z-score is less. It's actually more, but it's not as extreme as our cutoff point. So it is, so Z equals minus 2.08. And the cutoff point, Z alpha, was minus 2.32. And so we come here to have our sample score not in the shaded region. The sample score is in this white region. And so we have to fail to reject HO. Our sample score was not high enough to allow us to reject. And so this is a non-significant result. The null hypothesis stands. So if we don't reject it, the null hypothesis wins, and the researcher says this is not significant. Finally, going back and erasing everything one last time, let's give one more possible condition, and this is the condition in which the researcher doesn't know or doesn't want to predict whether a sample Z-score associated with population 1 will be higher or lower than population 2. So the researcher simply predicts that population 1 will not be equal to population 2, or that it will differ in some way. This is where we were looking for the word different. And the null, and this is the research hypothesis, and the null hypothesis, HO, is that population 1 is equal to population 2. And let's imagine now, we know we're doing a two-tailed test. And so our cutoff point, we know it's two-tailed because we have this word different. And in a two-tailed test with alpha 0.05, we know the cutoff, let's write that down, two-tailed alpha is 0.05. We know that the cutoff point is going to be, we've looked it up, so Z, the Z-score associated with alpha, is going to be plus or minus 1.96. And so we draw this into our distribution. There is Z alpha is minus 1.96. And again, in this tail, we have Z alpha is 1.96. We shade in both tails of the distribution. And so any score that falls in this region allows us to reject HO and gives us a happy researcher. Or in this region, same thing. We've taken our alpha and we've divided it between these two halves, and anything in this white portion of the distribution means that we fail to reject HO. The researcher will maybe be sad depending on what he hypothesizes. And so if our sample Z-score is, let's make it negative 1.99, that sample Z-score would then fall just barely into this region, minus 1.96 compared to minus 1.99. That's Z equals minus 1.99. It is in the shaded region of the distribution. And so since it's in this reject region, we reject HO, our null hypothesis, we cross it off, and the researcher's research hypothesis is supported. Now remember, this doesn't prove anything. All this does is give us one piece of evidence that the odds of getting a score of minus 1.99 just by pulling a sample out of this population are less than 5%. And that's what that probability less than 0.05 means. And that is the end of this little lesson.